Hey everybody, Dr. Pingle here. For this notebook, we're going to talk a little bit about taking point data and representing it as a raster. Now, there are lots of ways to do this. We're going to talk about 4 tools today. And to do that, I've got a data set here that I got from Baltimore's police department webpage, and they distribute a complete record of 911 calls. And I've grabbed the first 10,000 entries into that data set and cleaned it up a little bit and projected it. And so this data set is in UTM 18 coordinate system. Now here you see a bunch of points, a bunch of dots representing 911 calls in this period in Baltimore. If we zoom in on this, you can see individual little spots here, but when we zoom out, you can see that the dots start to sort of stack one on top of another. And you can imagine that the more dots that I have, the more likely this is to happen. Now you can get an okay sense of the distribution, the spatial distribution of these. You can sort of visually start to see where they're clustering and where they're not. But once they get clustered to a certain point, it actually becomes hard to tell which are more dense clusters. So for instance, is the center of this cluster more dense than that cluster, for instance? It's actually very difficult to tell. If you zoom in a little bit, you might get a better sense. You can see that this is a little bit more dense than the others and so on. But at this scale, it's quite difficult. And so this is why we use point to raster tools to start to get a sense of how well this is working. So the first tool that I thought we'd discuss is the feature to raster tool. So if we open this up, we get an option here for input features, and so we could either select this here, we could pull this open from disk if we haven't loaded it in, or we can drag and drop that. This next parameter here is field, and so this is going to be essentially what we're going to use to count. And we've got a number of different things here. To get a better sense of what's going on in this data set, we can look in the attribute table. There we are. And we can get a sense of what these things are. So we have a record ID, which is numeric. We've got a date and time. We've got a priority here, high, medium, non-emergency, and low. We've got these things sorted out by district. We've got a sort of a brief description here of what's going on here. So we could potentially develop categories based on this. We've got a call number, which is probably another unique ID. We've got an incident location, we've got a location, and then we've got latitude and longitude. And these were added on with a little bit of Python. They were included in the original data set, but just not easy to access. So that gives you a sense of what these things are. The field actually doesn't make too much difference in this case, so we're just going to go ahead and use FID for this. The output raster, you can put this wherever you want. Make sure you give it a reasonably good name here. I'm just going to save these things to an output folder. And we'll just call this feature to raster 0.tiff. Now the output cell size will be automatically calculated for you. My advice is to give this some thought. So you can see that this is 64.09. That is pretty close to 50, which given our coordinate system would be a 50-meter grid. If we run this, essentially what this is doing is this is going to encode a value here based on, in this case, based on the FID. And it's just going to fill in a square anywhere there was a dot. It's not going to do anything elaborate like count them. And so while you can change things like, we could set this to priority, for instance, so this is high, medium, low, not emergency. We could rerun this. And And so now we are getting a sense of what type these are. Now this is essentially equivalent to going into properties, um, sorry, going into appearance and changing the symbology and symbolizing based on unique values, right? So if we had changed this to priority, we're essentially getting the same kind of representation. And we could match these up if we wanted to. It's a little less important here. Anyway, so what happens if there's more than one dot in here? So if we look carefully, we'll find one here. So this is an example of we've got two dots in the same square, and the square was coded medium. And if we just inspect what was going on with that one, you can see that that was indeed medium. If we look more carefully still, we ought to be able to find a case where there were actually two different kinds within the same square. So here's an example. This square was tagged as medium. This particular dot was coded as medium, but this dot was coded as low. So the mechanism for how it's going to choose which color to shade it is a little bit it's a little bit hidden. It could be the first one, it could be the last one. You should regard that as unreliable. And so if you think there are going to be cases where more than one dot might end up in the field, you're likely going to want to use a different tool. So feature to raster is kind of a nice, I think of it as sort of a Swiss Army knife tool. You don't need to pay too much attention to whether you're dealing with points, lines, or polygons. But you're probably better off using a different tool. So the next tool that I want to talk about is point to raster. And there are equivalent for this for lines and polygons if you're interested in doing that. We're just going to use point to raster today. We'll use the same data set. The big difference between what you're looking at here and what we saw in the last one is that we get some additional options in terms of value fields, cell assignment type. Value fields actually is the same, so we could choose, for instance, priority again. And then we can choose a cell assignment type that corresponds to something else that we might want. Since priority is a text field, we only have two options. We can either do most frequent or we can use count. But if we chose a numeric field, for instance, FID is numeric. It's not a great example here, but we could, if we're using a numeric field, we could use sum, mean, standard deviation, maximum. When would this stuff come in handy? Well, we might have recorded something like the length of the call and or time of day, in which case we could do some statistics on that to try to figure out what the average call length was or the average time of day. We would have to be a little bit careful about that one since time of day is essentially circular, right? 11:59 at night is very near to 12:01 in the morning. But essentially, we would just use statistics to calculate these things, right? Mean, median, range, and so on. We also have another field here, priority. So this is a field that's used when the feature should take preference over another feature with the same attribute. I tend not to use this one very often. And then we have another cell size field, which is again auto-calculated for you, but you can choose that. So let's do an example of we'll use priority again here, and we're just going to run this. And so now we're using most frequent. We still have cases probably where we have more than one dot in a square. If we look at this, this is not, again, because we're using a fairly small cell size here, we're not getting a lot more information here than we got with the dots, right? It's a little bit, the symbols at least are not overlapping, so that's nice. But otherwise, this isn't a terribly helpful visualization. What's likely to make this a little bit more useful is making the cell size a little bit larger. So instead of 64 meters, we could try something like 250 meters, in which case these squares are going to start to get fairly large. And this is where most frequent really comes in handy, because now we definitely have cases where we have mixed pixels, right? In this case, we have two what are high frequency calls. This looks like maybe a little hard to tell, non-emergency call, a medium call, and low call. But because these two because there were two highs in this square, then the whole square gets coded as high. So you can see that it's purple and coded as high. So most frequent is actually a really helpful aggregator. If we crank our cell size up even further to 500, we can start to see that our pixels get quite large. And now we're starting to get a better look. Let me turn these dots off. We're starting to get a better look at what sort of the dominant call pattern is. So for most of the city, medium is our dominant call pattern, but we have some lows, we have some non-emergencies, and we have some highs, and you can see that. Now the other common one is going to be count. So what if we wanted to know where in the city are there most are there a high frequency of calls? So we could run this with count. We'll just hit OK here. And we would get something that looks like this. Now the symbology is going to help us kind of disentangle this a lot. So if we click on our layer and go to appearance, we could choose a symbology that maybe makes this a little bit clearer than just a gray tone. So we could choose something like this that would help us sort of see highs and lows. So this is a diverging color scheme. This wouldn't necessarily be a bad choice. We have choices to make in terms of things like whether we're using a classified scheme, something like this, where we might use natural breaks to decide how it looks, or geometric deviation, or anything anything related to that. We could change the number of classes to sort of bring out detail if we wanted to. And here you can see that by choosing a classified color scheme, we've actually shifted to this kind of yellow to red, which is kind of a nice way to do it. We're also, by default, and this is a nice addition in Arc Pro, we're suppressing cells with a 0 value. So you can see that there were no calls in these squares, which you can see corresponds to a park. And so we just make that transparent, which is kind of a nice way to do it. If you have other layers, you can do other things, bring things into transparency if you need the base map, for instance, to shine through, all those kind of normal visualization options that you're probably used to already. With that said, let's take a look at another tool. So point to raster is quite effective, but you can see that it's actually also fairly blocky. There are some things you can do to make that a little bit nicer. So for instance, you could change that to cubic, which is kind of a nice way of hiding the blocky nature of this. But it's essentially working the same way. It's applying a smoothing interpolation algorithm just for visualization's sake, but it's not actually changing the underlying data at all. But it can be a nice quick way to improve the visualization. Another way to do this, though, is to actually use a tool that's going to blend these in there. So instead of relying on a resampling or an interpolation to smooth things out, we're gonna smooth out the data itself. So to do that, we would run a different tool. So these are density tools. There are two that we're going to talk about today. We're going to talk about point density first, and then kernel density. So point density works quite a bit like the count feature that we just played around with. So if we use our original data set, we can output a raster here. So we'll just call this point density. We've got a few other variables here that are going to make a big difference. We've got an output cell size. So again, this is automatically calculated for you. You may want to change that. So in the last example, we used something like a 500 meter block size. And I would suggest sort of iteratively playing around with this to see what creates the most visually appealing pattern. The other thing the thing that is going to differentiate point density from the last tool is that it's actually going to count things within a radius. So the idea here is nearer things are more related than distant things. If I get what the pattern of data that I'm seeing here is just sort of one instance of things that happen, but in another year, maybe the same overall pattern appears, but the addresses or the locations are slightly different. And what we're trying to get at with this spatial analysis is what's the underlying pattern of the data. So what we want to do is sort of count anything within a range. Think of this like a moving average, and it's going to smooth out a lot of the discontinuities that we just saw. So the way that this moving average is calculated spatially is we have what's called a kernel or a neighborhood. We've got a few different examples of how you can do this. Most of the time you're going to want to use circle, so you're going to count anything within a certain radius. Occasionally you may want to use a rectangle, and I would encourage you on this notebook to play around with both of these to sort of see what the output looks like. The radius is going to be the most important thing here. So the radius is going to say, how far away do you want me to calculate that moving average? The longer the radius, the smoother this is going to be, but maybe some of the more local patterns are going to start to get hidden. You can also specify the units in terms of cells, so in terms of pixel distance. So a radius of 1, given our output cell size, would effectively be a 500 meter radius. So you can use whatever makes the most sense to you. I would probably keep this on map distance, but this would work either way. The other variable here that makes a difference is the population field. For our data set, it doesn't make much sense. But for instance, if there were a column that indicated how many people were involved in this particular call, is this just a single person calling? Is it, is the trouble that's happening related to 5 people or 100 people? We could potentially weight each observation by a number that indicated the importance of that observation, maybe however many people there were, or so on. So we don't have a population field, so we're not going to need that, but it's a good thing to keep in mind. So if we go ahead and run this, just to keep in mind, our output cell size here is 500 meters. Our radius is also going to be 500 meters. You'll notice that point density does take just a little bit longer to run than the point-to-raster tool. That shouldn't be too much of an issue for the data set sizes that you're working with. But if you're working with very, very large data sets, you might want to keep that in mind. In this case, I'm going to turn these off here. So here you can start to see a pattern, and I want to code this according to, or I want to symbolize this according to the same color scheme that we were looking at before. So we'll use this yellow to red. It's nice for showing intensity patterns. Again, by default, the default visualization had suppressed this lower category. You can go in and change this on your own to help hide those 0 values, which can really help bring out the detail here. Okay, so how does this differ from the last set of observations that we looked at? Well, it's not too different. So we'll turn this back on. There's our point to raster. There's our point density. But you can see that we've actually smoothed things out a good bit here. We'll use our swipe tool to compare. So compared to what we were just looking at, the pattern is a little bit smoother. These kind of larger values kind of in here get kind of buffered out a little bit effectively. And so we just get a nice smoother value. And again, we can also come in here and change the resampling type to smooth that out further, which might be visually appealing. If we did that on our last example and changed that also to bilinear, you can see that we're seeing again a similar pattern here, and in effect, let's see here. There we go. Very, very similar pattern with a little bit of extra detail in the point density. Okay, now I would encourage you to play with we go. Let's load that back up in here. So we have to set this to 500 as an output cell size. The larger the radius, the more aggregated your results are going to be. So if we double that and set that to 1,000 meters, and we run this again, what kind of pattern are we going to see here? Well, first of all, let's set these back to the same resampling type so that we're comparing apples to apples. And we will change the appearance again just to make sure that they're visually similar. All right. So what's the difference between our 1,000 meter buffer and our 500 meter buffer? Well, in comparison, you can see that the 1,000 meter buffer, which is what we're seeing here, is quite a bit more generalized. So we've kind of smoothed out again a lot of what we were seeing. There's again no real right or wrong answer here to what that number should be. It's kind of whatever number brings out the pattern that you're trying to show in the data. And so I would definitely encourage you to experiment. If we go the other way, so if we run this tool again, but this time set our radius to something quite a bit smaller, maybe let's say 150 meters. We get a pattern that looks quite a bit different. All right, so here we're comparing to it to the original 500 meter buffer, and we're eliminating a lot of. Let me just turn this one off. We're eliminating a lot of what we had seen before. Part of this is the number of classes. So if we crank this up to something larger, you can see that the distribution here is just quite a bit blockier than what we saw before, right? So this is our original 500 meter buffer. This is our 150 meter buffer. So the dots are just a little bit more isolated, and the pattern just looks a little bit different. Now, again, part of the pattern, what we're seeing here, depends on that density count. And so how you choose to visualize this with your symbology is going to change it. But even apart from the symbology, this is just a more discrete pattern. And in contrast, compared to our 1,000, you can see that our 1,000 is much less discrete, right? So hard to make out individual points here. You're really looking at sort of big picture pattern. And here, these individual little hotspots show up. All right, so the last tool that I want to talk about here is the kernel density tool. So the kernel density tool is another way of doing this. This is probably the most common way of running these numbers. We'll change this to kernel density. Just for consistency, we'll use an output cell size of 500 meters. Now, one of our choices here is to set this output cell values from densities to expected counts. Either of these values kind of produce relatively similar results, but I would encourage you to play around with that a little bit and see that for yourself. This method of calculation is actually quite important. Planar is going to treat your points as if they are on a plane, so just flat Cartesian coordinates. That's appropriate if your data has been projected like ours has. But if we were dealing with the raw latitude and longitude values, this would not be appropriate because the distance between 1 degree of latitude is not the same as 1 degree of longitude at this latitude. And in fact, at no latitude. But it's extremely, it's a relatively large effect here. And so you'd want to make sure that either your data is projected or you're using this geodesic method of calculation. This is always going to be the most accurate, but it's also the most computationally expensive. If your data has been projected, and it's appropriately projected, then you can just use planar and things are going to turn out okay. If you're dealing with straight latitude and longitude values, then you're going to want to make sure that you're using a geodesic calculation. One of the things that you're not specifying here is your kernel shape. So this has a quadric kernel that weights things a little bit differently than point density. So while point density essentially sort of buffers around and counts anything within a certain range, like a moving average, this is effectively something like a weighted moving average, so that nearer observations are given more weight and more distant observations, while counted, are not counted as much as near observations. There's a blank that's missing here, that's search radius. So if we click on this, you can actually see that the default search radius is calculated automatically. If you just go ahead and run this, you'll get relatively reasonable results based on that calculated search radius. And again, we can make some comparisons here to what, compared to what we did before by changing this to this color scheme. All right. So we'll just uncheck some of our old ones to make sure that they're not coming through. When we have transparency in here, it's easy to, especially the same color scheme, it's easy to let layers underneath influence what we're seeing on the top. This is our resulting pattern for the kernel density analysis, and what we're seeing here is again, same representation. What are the sort of spots where there is a high density of 911 calls, whereas they're low density? This sort of helps us see spots within the city. Again, same idea, moving average, but a weighted moving average. We can change the way that this is calculated by using by specifying the search radius. So for instance, in the last example, we had specified a search radius of 500. Because the weights are allocated differently, you won't see a perfect correspondence here, right? We might count things up to 500 meters, but at 500 meters, maybe they're not counting very much at all. So if we run this again, we should see some mild differences in how this looks. Oops. Okay, so this is our new one calculated with a 500 meter bandwidth. This is our old one. We use the swipe tool again. This is our old one. That's our new one. Compared to what we just saw, our new one is a little bit more discrete. The one with the automatically calculated bandwidth is a little bit more generalized. And so that's telling us that probably the automatically calculated one was using a larger limit. So we'll just do one more here to illustrate that. So again, output cell size will be consistent at 500. And then our search radius, we're going to set to something quite high. We're going to set this to 2500. All right, so comparatively, we could change the color scheme here, but you get the idea. Comparatively now, we've really aggregated to a very, very large degree. We're hardly seeing any detail at all. We might change that to 1250. Here we go, starting to see a little bit more pattern jump out here. 1000, we should start to see a little bit more local pattern. Okay, and we'll just change this one to the color palette that we've been using. Here we go. All right, so compared to what we were looking at, now we've sort of really pushed our pattern out quite a bit. And again, a lot of this is in symbology. We could change this to geometric interval. This is going to change the pattern of the data quite a bit. We could change this to standard deviation. So many ways in which we can manipulate how this looks. And so for this reason, a lot of the point density and kernel density tools are sort of regarded as good exploratory data analysis. It's a good way to sort of start to get a handle on what's going on in our data. But because it's so easy to manipulate the final appearance based on the factors that we've looked at, the search distance and the symbolization, we often will use something called cluster analysis when we need to make sort of hard decisions about that. But that doesn't mean that these aren't valuable tools. They definitely are. They're a nice way to sort of, again, explore your data, get a handle on it, and in many cases, it is probably appropriate to publish these. All right, so with that, we'll wrap things up. For this notebook, you'll use these 4 tools. Most of the time, kernel density is going to be your go-to, but each of the other 3 have value, and so it's good to know when to use those and when you might not want to use those. All right, thanks for listening. We'll catch you next time.